What up, people? Welcome back to the second episode in the Natural Language Processing for Tensorflow tutorial series. This episode we're going to try to cover actually making the model and running it and training it. And since in the last video we made all of our input data and our labels, we should be able to do that. When you run TensorFlow's embedding lookup function, what it's going to do is it's going to take a word, WT, and we already did this. So these words are going to be represented by an index number of vocab. So we have all of our indexes inside of our vocabulary. So we could pass it the 32nd index, and that's the 32nd word inside of our vocabulary. What it'll do inside the function is it'll create a vector that is of length vocabulary, and it'll have it be all zeros except for a 1 in that spot that we set. So what, 32nd? So we'll have 0, 0, 0, 0, 0, and then 1 in the 32nd spot, and then a bunch more zeros. It'll take this, and it'll multiply it by this embedding matrix, and it'll extract that single row that it needs, and that would be the word that we had represented as an embedding. So it's a dense representation of that word. So what do we do with this embedding after we extract it? Basically what we want to say is, what's the probability of outside word given the pivot word, or given the word that we started with, this WT. So what you say is, what's the probability of another word happening given this embedding right here? So what you could do is you could say, what's the probability of every single word inside of our vocabulary given that word? This would be, again, very computationally expensive if you have something like 50,000 words in your vocab. So another solution to this is something called negative contrastive sampling, and that's what the TensorFlow examples use on their website, so that's what we're going to use. And basically what this says is, you set a given sampling number, and you say, instead of looking through every single word inside the vocab, you just say, here's 64 random samples that are just noise, and then you also give it the actual label, so what the actual next word is, and you train against 65 samples, and instead of it being 20,000, 50,000 samples, and that basically reduces the computation time a lot, and it's basically a trade-off between accuracy and computation time, and they found that this actually works a lot better. So that's what we're going to actually use when we go to write this up right now. All right, we're going to start back off in the same file that I left you in the last video, and we're just going to make the network now. So I just want to note that I still do have this data cutoff here. Delete this later. This is just for running it pretty quickly, but as soon as we get this all finished, you can take that off. I do also want to note that the way that I wrote this is a little bit memory intensive. So if you do have to end up taking, if you do end up running to memory issues, then go ahead and do a df sample. You can do that it's something like so instead of doing this, you do something like df equals df.sample, and then you can put a set number of rows that you want to extract from the data frame, and that'll basically do a random sample. So you're grabbing things from both of these, and it's not in any sort of order. That's what you probably want to do if you run into some memory issues. Or you could help me fix this, because I think this probably does need to be fixed. So let's get right into it. We're going to create a function to build Word2Vec. So def build Word2Vec, and we're going to start off with our placeholders for our model. So we need one for our pivot words, because those are our x's. So we'll say x equals tf.placeholder, and we want those to be int 32s, and the shape of these is going to be none, comma, and then just close it. So basically it'll be none will allow for like a variable batch size, and then I'm going to name it. I might make a video a little bit later on how to visualize these. So for now, let's name them so that when we go to do that, it won't take us very long. And we're going to make a second placeholder for our y's, which are our target words. And these are going to be the same thing. Except for we're going to call these the target IDXs. All right. And now we're going to make our embedding. So like we said earlier, our embedding is vocab size by embedding size. So embedding equals tf.variable. And we're going to make it tf.random uniform. We're going to open this and say vocab size by embedding size. And they're going to be from -1 to 1. And I am going to name this one too word embedding. Cool. So I didn't declare the embedding size, I don't think. So let's do that down here. So embedding size equals, we'll set it to 128. Oh, embedding. There we go. That's a little bit better. So instead of doing softmax, we said we're going to do the NCE. So now we create NCE weights and NCE biases. The NCE weights are going to be the same shape as our embedding matrix, and the biases are just going to be vocab size length. It's just one dimension. So another tf.variable, and we're going to say tf.truncated normal this time. And this is going to be vocab size by embedding size. -1 to 1. Oh, actually, this one we're going to do a little bit differently. We're going to do it, we're going to say std dev, so standard deviation. We're going to say tf.square root 1 over embedding size. And then we're going to name it. I'll make sure you can see this. I'll leave it there. It's fine. Getting a little crazy. All right. So those are our weights, and then we make our biases. So NCE biases equals tf.variable, tf.zeros this time. And that's going to be vocab size. And the name is going to be NCE biases. Perfect. And I'm just going to add a couple comments here. Make our word embedding matrix. So we have our embedding matrix, we have our weights, we have our biases for our loss. Now what do we need to do? We need to make sure we have something to look up that pivot word. So our pivot is going to be an embedding lookup. We mentioned it earlier that what you do is you pass the index to this function as well as the embedding matrix, and it'll look up that row vector that we're trying to extract. So you call tf.nn.embedding lookup. You pass it the embedding, and then you pass an X, and we'll name that word embed lookup. Up, pivot, word embedding. Perfect. So now we're ready to calculate our loss. So with we won't do that for now. We're going to say train labels equals tf.reshape y into tf.shape y0 by 1. Basically what this is doing is it's going to expand the dimension by 1. And actually, that's not true. What it's doing is it's setting the shape to be an actual concrete shape. Because we pass it in with none, this handles variable batch sizes. But when we go to do this NCE loss, I've run into issues when you pass it none, it says that it can't do it when you're doing it with none, so you have to change it to what exactly the shape is. So we're just reshaping it to exactly what it already was, which is its own shape, comma 1, because that's all it is. We're just passing it a 1. So here we go. So the loss, let's do this. So tf.reduceMean of tf.nn.nce loss. And this has a bunch of parameters. So the first of which is weights. So weights equals our NCE weights that we already made. The next is the biases, and that is NCE biases. Labels is the train labels. Inputs equals pivot. Num sampled equals num samples. We have to create this variable, but that's going to be the number of samples that we choose to train the loss against. So instead of doing it against the whole vocab size, we're going to do it against the number sampled. So then num classes equals vocab size, because that's the number of potential classes. And then num true equals 1. And we're going to go ahead and go back up here where embedding size is. And we're going to write num samples equals, we'll do 64. So we've done that. Now we just need to get our optimizer. So optimizer equals tf.contrib.layers.optimize loss. And the reason I'm using this function is so that I can do gradient clipping, which you could probably do a whole video on, but I've just seen people doing it, so we're going to go ahead and just do it this way. And this takes loss tf.train.get global step, and that'll get the global step, so how many iterations it's gone through, and TensorFlow keeps that number in the background, and by calling that function you get the global step. So learning rate atom is the optimizer we're going to use, and then clip gradients equals 5. And then we're going to say name equals optimizer. We're just going to add a couple comments here. Boom, so that is how you do all of that. And because this is a function, we're going to end up having to return all this stuff. So let's say sesh equals tf.session. I got a feeling I'm missing something up here. Yeah, there it is. And we're going to say sesh.run tf.global variables initializer, boom. And that'll initialize all the variables, and then we will return optimizer loss x, y, and sesh. And there you have it. That is our Word2Vec graph. All right, one more thing I wanted to note is that I did have a typo here. So make sure that you have global here instead of whatever mess of words I had. And then also make sure you instantiate a learning rate. We forgot to do that. So just say learning underscore rate equals 0.001. And we did use that again in the optimizer down here. So after we do that, we can go outside the function and we can write optimizer loss x, y, and sesh equal build Word2Vec. And if this runs, then we know we're good to go. Now, in the next video, we are going to cover how to train the model and how to get the word embeddings. So I want to make sure I keep these videos a little bit shorter because I know that these are spilling on and going pretty long. And I know this is a lot to take at once sometimes. So, oh, and it worked. So we know that we're good to go. So I will see you guys in the next video. Thank you very much for watching.